This example now is a little bit more sophisticated because you see we have a set A, so our first ingredient, with -1, 0, and 1, and nothing in between. Right now we are going to choose sets, but to consider the entire range of the same. How do we express such a set? Well, let's see. It has an initial point here, and there is a final point here, final. And I want to include everything in between. Just to make it more clear, let's consider the initial point 3 and the final point 5. The middle point then is 4. Now, notice that it is 1 unit apart. So, from 4 to 5 it's 1 unit, from 4 to 3 is another unit. This entire set of points that you see here, between 3 and 5, excluding 3 and 5, is analogous to the following idea. Imagine that we have here a circle. We have a circle, and the intersection of this circle, of radius 1, the intersection of this circle with radius 1 with the horizontal line, excluding the initial and final points, is exactly those set of points in between. Let's call it B1 of 4. So here's the radius, here's the middle point, which is equal to, so this symbol here is an abbreviation for the set, which comes from 4 minus 1, well, which is 3, up to, so it's the entire set of points from 4 minus 1 up to 4 plus 1, okay, excluding it, okay, because we are excluding the 5. Why am I rewriting the sets from 3 to 5 using the reference as a middle? Well, because soon I'm going to act with the functions s, c, l, and r, and it will be useful to track the middle point, where it goes, okay? So I'm going to explicitly write the set which was from 3 to 5. I'm going to rewrite this instead in this manner, because this emphasizes what? The middle point here and the radius here. In general, these sets can be written as follows. We call B epsilon of x to be, so this symbol here is by definition, so by definition, an abbreviation for x minus epsilon and x plus epsilon, where x is the middle point that you must specify, and epsilon is the radius of that circle, okay? So, with this concept in our hands, let's now act with our functions on this thing. Let's start with just s function. We see here the s function in pink. We find here on the horizontal axis x, the input of our function, and on the vertical axis, the corresponding images. Note that our function s is a line. It is then a bijective function, okay? With domain R and codomain R as well. In this smaller diagram, you see our set as a particular case of our set B here. Our set B, which has radius given by 0.5 and is centered at 2. The set here is schematically represented here. Center at 2, and radius of 0.5. So 0.5 to the right and 0.5 to the left. Now, this is a set of points, and so our s function will map each one of those points into their corresponding images that you see here on this graph, from 3 to 5, or here schematically, s acting on, well, the input set, okay, is another set. That another set is a set here, from 3 to 5. Or should I say, in other words, so the s acting on this initial set is a set B, let's look at the picture, center at 4, with radius of 1. So what we see here is exactly what we anticipated. The middle point will shift to the right, okay, as you see here. So here's the initial set, and the final set will shift to the right, because now it's 4. But more than that, this initial set is small, but the final set is much wider, okay? It's twice as larger. You can imagine now for a moment what would happen if this initial set with radius 0.5 was not centered at 2, but instead centered at 0. The middle point 0 will not change, because 2 times 0 is 0 again. But however, the remainder points, well, we are going to be stretched, and the set becomes twice as wide, okay? As a final example, let's consider now a function which is not a bijective function, just like our mountain function that we saw previously. So we now are going to choose this function here, the pink one, which we recall as, well, f of x is equal to, well, 1 minus x squared, which is not bijective. The starting set is centered at 0 with radius 0.5. And we observe that for this f from 0 to 0.5, each one of these points here is mapped into these points here, okay? And all those in this region here are also mapped into these points here, the same set. The reason for this happening is because it's not bijective, it's not a one-to-one function, okay? So whether you consider x's that are positive, the corresponding negative ones are mapped into the same value. So those two pieces, the negative piece and the positive piece of the starting set B, are mapped into exactly the same points. Notice when the function is one-to-one, you need not to worry about these kind of details, because with a bijective function, each point in the initial set B is mapped into a distinct point. This is no longer the case when the function is not one-to-one, like the mountain here, okay? So be careful when the function is not one-to-one, and when it's one-to-one, it's quite easy to work with, okay? Now, let's move on.